Hi everyone, this is Phil from statisticsmentor.com, and today we're going to be looking at the relationship between the F distribution and the chi-square distribution. First, I'll present the main result, and second, we'll look at three simple examples. Okay, now the result is this. If we take two chi-squares, two independent chi-squares, say the chi-square with p degree of freedom, divide it by its degree of freedom, and divide that whole thing by another chi-square, which I said degree of freedom q, and divide that chi-square by its degree of freedom, then what we can see is that this new variable will follow a F distribution with degree of freedom p and q. So to repeat, if we take the ratio of two chi-squares, independent chi-squares, divided by their respective degree of freedom, that new variable will be F distribution with degree of freedom p following the numerator and q in the denominator. Numerator, denominator. Recall that this is different to the other way round, like this, different things. Okay, so that's it. Note that these two chi-squares must be independent for this to hold. So what you want to do now is just to jot this result down on a piece of paper, and then we're going to turn and look at three examples. Okay, question 1. Consider independent standard normal variables zi, each of which are standard normal, I normal with mean of 0 and the variance 1, and for I 1, 2 all the way to 10, state the distribution of a z1 to the power of 2 divided by z2 divided by the power of 2. Right. Now, so what we can see straight away is that the numerator, that involves standard normal squared, and the bottom involves a standard normal squared. And remember, when we see standard normal squares added together, that points to a chi-square. In this case, we've got z1 square, and that is just one standard normal which is squared. So from previous results, we know this is a chi-square 1. z1 squared is chi-square 1. z2 squared is also chi-square 1, because there's only one of z in the bottom. Okay, now obviously these two will be the same if we divide each by 1. Why divide each by 1? Because now it is of the format a chi-square divided by its respective degree of freedom, and we're looking at one chi-square over another chi-square, and these two chi-squares are independent because it tells us in the question that these z's are independent, so z1 is different from z2, so this will be f1, 1. Now some of you may well be thinking, well, isn't the bottom bit chi-square 2 because you got z2? I get that every year. Now the answer is no, because what you're seeing here, these subscripts are only like labels, they are not telling you how many z's there are. So z1 is just standard normal, as is z2 is a standard normal. Okay, and the fact is that at the bottom we've just looked at one z. It's not like of the form z2 squared plus z3 squared, which would be two of these z's, which would be chi-square 2. Okay, so that's the explanation. Next one, and basically I've explained this one as well. B is z3 squared divided by z9 squared. Hopefully you can see that it's just the same thing, f11, because there's one z squared on the top, one z squared on the bottom. The fact that the subscripts are different to the part A is neither here nor there. 3 and 9, I could have had 5 and 6, could have had any old thing, so long as it's within 1 to 10, and so long as they're not the same. Okay, so it answers both A and B. Both A and B are F1, 1. Now, part C. Now, when we see, as I said, a ratio of standard normal squares and added together, we're thinking chi-square in the top, in each top and bottom. So here you've got z1 squared plus z2 squared, so that suggests a chi-square 2. So if we write, let's see, 3 over 2, let's write down the question, z1 squared plus z2 squared, both standard normals. We know that if we divide by 2, then this whole thing here, z1 squared plus z2 squared all over 2 will be chi-squared 2 divided by 2, right? Now, but then I've changed the top, which I don't want to do. So if I divide this by 2, I should multiply by 2. So it balances out, this cancels with this one. Likewise on the bottom, so if you didn't get my explanation for this one, let's repeat the same thing for the bottom. Bottom has got 3 z's all squared and added together. Now since these z's 3, 4, 5 are not repeated up here, this is only 1 and 2, that means this here forms a chi-square 3, which is independent of that thing at the top. So we've got z3 squared plus z4 squared, 4 squared plus z5 squared, no, z8 squared. God, my eyes are deceiving me, I've written an 8 there. Okay, well it doesn't matter anyway, but z8 squared doesn't change a thing. If we divide just this bit here by its degree of freedom, well, because we can see that this is going to be chi-square 3, so if we divide that by 3, then we also multiply by 3 to nullify that effect. So in this essence, what we have then is 3 over 2, and then on the top what we have is this bit here is chi-square 2 divided by its degree of freedom, which is 2, and we've multiplied that whole thing by 2, and the bottom is a chi-square 3 divided by its respective degree of freedom 3, but we multiply by that bottom by 3 as well to balance it out. So what we could see in this center bit here, this is these two chi-squares independent because the z's here do not share any common z's, and yeah, so it is therefore an F2-3 distribution, this bit here. Moreover, you can see some terms cancel. 2 cancels with that 2, 3 cancel with this 3. So what we're left with nicely is F distribution with degree of freedom 2, 3. Finished. Alright, so that one's slightly more complicated. You might want to read through that again, but if you want an even more complicated one, in the next video we'll do question 2 part A, which is, I can't remember where I got from. Is that from a past paper? I don't know. Anyway, if you're interested, follow me over there. Okay, all for now.